All right, in this video, we're going to look at what are called cofunction identities. And the first thing I have here on the page is just how you would show these cofunction identities. So again, the cofunction identities where I'm going to highlight in yellow. It's this one here, and then along with these two groups of two. Those are called cofunction identities. So the sine of 90 minus theta is equal to cosine of theta, and the cosine of 90 minus theta is equal to sine of theta. So from right triangle trigonometry, you can see that from this blue triangle here. I'm just going to zoom in, right? I've got a right triangle with sides labeled. The two acute angles are theta and 90 minus theta, so that all three angles add up to 180. And by the definitions of sine and cosine, I have that cosine of theta equals a over c, adjacent over hypotenuse. But that's also the sine of 90 minus theta if you just switch reference angles. And similarly for sine of theta. And then to get the other sets of two, you want to use the fact that the reciprocal of sine is cosecant and the reciprocal of cosine is secant. So by reciprocating both sides, you get that identity. And then the tangent and cotangent ones, you can either get, again, right from this right triangle here, right? So that we maybe just examine that. The tangent of 90 minus theta, the tangent of 90 minus theta according to the right triangle would be, by the definition of tangent, it would be a over b. Right, so this is a over b. But the cotangent of theta is adjacent over opposite, which is also a over b. Okay, so in any case, from right triangle trigonometry, that's how you can get these identities. I'm going to explore how you would get these using the unit circle in case you're coming to this video haven't seen the unit circle. So first, I want to show you an important identity that shows up a lot. And knowing this identity will kind of help you very often further in your study of trigonometry. So again, let's say this is the unit circle. I'm going to call this point A. And because it's the unit circle, there are a couple ways we can think of labeling this point here. So I'm going to call this side A and this leg here B. So the name of that point could be A comma B. But if I imagine I rotated angle theta in standard position, I could also name it, again, because of unit circle trigonometry and the new definitions of cosine and sine. Cosine of theta is the x-coordinate. Sine of theta is the y-coordinate. Now imagine rotating the exact same angle, but in the negative direction. So I'm going to call this here negative theta. What that means is this point here, let's call that point B, it could have the name A, but this time negative B would be the y-coordinate. And of course, using trigonometry, we could name it cosine of theta, cosine of negative theta. Just rewrite that. Cosine of negative theta, sine of negative theta. So this one diagram gives us an identity because we note that the x-coordinates of both of these points are the same. So that must mean cosine of negative theta is equal just to the cosine of theta. So there's an identity. And on the other hand, the y-coordinates, b and negative b, are opposite. So that must mean that this is the opposite of this. Sine negative theta is the opposite of the sine of theta. These identities I'm going to circle in green. Okay, those are important identities. Essentially what that says in terms of an algebraic definition, it says that cosine is an even function. Okay, in another video I can explain what that means, but just as a kind of to throw in the jargon, this says that sine is an odd function. Okay, and those have definitions and graphical implications if you're thinking of graphs. But in any case, I'm going to use those identities down here. So let's kind of look at the cofunction identity here, sine of 90 minus theta, cosine of 90 minus theta. Let's just do a quick exploration just to see if this actually even works. I mean, whenever you have an identity, it's important to just, pick an angle for an actual value for theta and just see if it works. So according to this, it says sine of 90 minus theta is cosine of theta. So let's see. This would claim that the sine of 90 minus 100 degrees, the claim is that's the same as the cosine of theta, which is a cosine of 100 degrees. And on the other hand, according to the other cofunction identity above, cosine of 90 minus theta should equal sine of theta. So that would mean that the cosine All right, so let's just kind of simplify this a little bit because I want to use those identities. 90 minus 100 degrees is negative 10 degrees. So I could also say that this is the sine of negative 10 degrees. And similarly, this is the cosine of negative 10 degrees. So I'm going to draw this picture. So let's start with this 100 degrees. Let's rotate 100 degrees on the unit circle. That brings us somewhere around here, let's say. Okay, that brings us here. If that's 100 degrees, that must be 10 degrees. Okay, and that point there, we'll call that point A. That can be expressed as cosine of 100 degrees, sine of 100 degrees. Okay, and make a right triangle here. Note what that means is that this here is, this must be 80 degrees there. And that means this also is 10 degrees right there. Now I'm gonna for the kind of the other part of this, I'm gonna draw in. I'm gonna represent not 10 degrees, but not negative 10 degrees, but actually I'm gonna use my identity up here. So we know that the sine of negative 10 degrees, the sine of negative 10 degrees must be the opposite of the sine of 10 degrees. And the cosine of negative 10 degrees must just be the same as the cosine of 10 degrees. Okay, so I'm going to draw 10 degrees rather than negative 10 degrees because it's going to give me a right angle. And the right angle is going to be useful in what we're going to see. So here is a rotation of 10 degrees. Okay, that means this is 80 degrees. And if I call that point B could have coordinates cosine of 10 degrees, sine of 10 degrees. But more importantly, we want to relate, right? We actually want to relate the coordinates. So what we can say is that if I call this x coordinate A and this y coordinate B, this here is clearly a 90-degree angle. Okay, and the reason is because, well, this is 10 degrees, and then you rotate to the red, you get, you're rotating 100 degrees. To get from 10 to 100, you rotate 90. So that's a right angle, which means that these two triangles are congruent. Again, we're in the unit circle, so that's a 1, that's a 1. And the angles are clearly all identical. So that must mean that this side here I can call negative B, and this side I can call A. And so then we can just note that A is known as two things. It's known as the cosine of 10 degrees, but it's also known as the sine of 100 degrees. Okay, and the cosine of 10 degrees, we note, is also the same as the cosine of negative 10 degrees, which we see above here. So the cosine of negative 10 degrees from the diagram is clearly equal to sine of 100 degrees. So that checks out. And then b, on the other hand, b is equal to, well, it's the y-coordinate of point B, so it's equal to the sine of 10 degrees. And negative b is equal to, it's the x-coordinate of the left triangle, so it's the cosine of 100 degrees. And so now we can see that b is equal to the cosine, that b is equal to the sine of 10 degrees. So that means that negative b is equal to negative sine of 10 degrees, but that's the same as sine of negative 10 degrees. So negative b equals this, negative b equals this, so that justifies that equation. All right, so let's just do the formal proof. I mean, now that we know, we sense that it works, and it's actually a lot more, it seems to be taking a lot more effort to show what might be more aptly expressed just from the visual itself. But just to kind of end this with an overall explanation, again, the claim is that the sine of 90 degrees minus theta is equal to cosine of theta, and the cosine of 90 degrees minus theta is equal to sine of theta. So let's see if we can figure this out. Let's call this angle. Let's call this angle negative theta here. Let's call this point A. So if that's point A, let's call this x-coordinate A. Let's call this y-coordinate, I'm going to call it negative B. And I can name this point A, negative B. I could also name it cosine of theta, or cosine of negative theta, sine of negative theta. Okay, so how do I get 90 degrees minus theta in play? Well, you want to think of this here as, you want to think of 90 degrees minus theta really as negative theta plus 90 degrees, because when you add 90 degrees, it means rotate counterclockwise. So if you rotate counterclockwise by adding 90 degrees, first of all, you create a 90 degree angle between these two, right? So this here is a right angle. By definition, you added 90, which means that this angle here is 90 degrees minus theta. When I say this angle here, I mean this one in green. Okay, and so when we create a right triangle, we notice a couple things. First is these two triangles are congruent. Again, we're in the unit circle, which means that if this is side A here, this whole thing here, side B must be that right there. So I can name this point B. Its x-coordinate is B. Its y-coordinate is A. Okay, because the triangles are congruent. And the side opposite the 90 minus theta has to be the same length in both triangles. So again, if this is 90 minus theta, that must be theta. So we can see that this would be B and this up here would be A. So now let's just equate them and see what we get. So, the last thing is that point B here is can be named as B comma A, which is also cosine of 90 minus theta. as the x-coordinate, and the y-coordinate is sine 90 minus theta. All right, so now we note that there are two names for A, right? A is, let's go down here. A is known as both the cosine of negative theta, and it's also known as the sine of 90 minus theta. But a cosine of negative theta is the same as the cosine of theta by this identity up here. And similarly, there are two names for angle B, for length B. Length B is known as the cosine of 90 minus theta. And since negative B is the sine of negative theta, and the sine of negative theta, according to the identity up here, is the negative sine of theta, we can see that negative b equaling negative sine of theta means that b equals sine of theta. So in both cases, we see cosine of 90 minus theta is the same as sine of theta, and the cosine of theta is equal to the sine of 90 minus theta. And those are those cofunction identities. All right, so this was a long kind of exploratory video of this identity. I think, very often if you're in a pinch, I would just anchor your understanding to this right triangle. The unit circle exploration is fine. It's a heavy lift for, just an identity that you can probably rediscover here. But the point is, it works for any angle, no matter what the angle is, even if it's beyond 90 degrees. This video produced another and key identity here. Cosine of negative theta and sine of negative theta have important uses beyond whatever course you're in. So in any case, if you are working on a book problem or something and find this helpful, great. Otherwise, just note these identities and try to commit them to memory, or try to rederive them on your own.